What specific problem does your method aim to solve regarding LLMs and mathematical problem solving? And how does this address limitations of existing approaches?
Our method specifically aims to enhance the mathematical problem-solving capabilities of large language models, LLMs, by integrating reinforcement learning from human feedback, RLHF, with external tools, addressing their limitations in complex reasoning tasks that require multi-turn decision-making. Existing approaches primarily relying on supervised fine-tuning, SFT, and synthetic data generation often fall short in accurately performing basic arithmetic and symbolic computations, as evidenced by their struggles on benchmarks like math and GSM-8K. By formulating the learning process as a Markov decision process, MDP, and developing multi-turn direct alignment algorithms, MDPO and MKTO, our method allows LLMs to effectively incorporate external messages and reason based on both prior interactions and tool outputs. This approach not only improves the model's performance on mathematical tasks, but also leverages the strengths of RLHF to learn from both successful and unsuccessful trajectories, thereby enhancing sample efficiency and overall reasoning ability. Our empirical results demonstrate significant performance improvements over standard SFT models, showcasing the potential of our method in overcoming the limitations of previous techniques.
How does the proposed method work? Illustrate step by step, including the MDP formulation and the key components such as actions, states, and observations.
The proposed method operates within a Markov decision process, MDP framework, where the learning process is structured into a series of interactions over multiple rounds. Initially, a prompt, X, is sampled as the starting state, S_1. At each step, H, the agent observes the current state, S_H, the history of interactions, and takes an action, A_H, based on a policy, Pi_H. The action consists of a reasoning step, F_H, and an execution step, E_H, G, writing Python code. Following the action, the environment returns an observation, O_H, which is then used to transition to a new state, S_H+1, that incorporates the history of actions and observations. This process continues for H rounds, culminating in a trajectory, tau, that captures the entire interaction sequence. The method emphasizes the integration of external messages and the optimization of actions through multi-turn direct alignment algorithms, MDPO and MKTO, which enhance the model's reasoning capabilities in mathematical problem-solving tasks.
Can you provide a simple yet illustrative example that demonstrates the inner workings of your algorithm in solving a mathematical problem using external tools?
An illustrative example of our algorithm in action can be seen in solving a mathematical problem from the GSM-8K dataset, such as Natalia sold clips to 48 of her friends in April, and then she sold half as many clips in May. How many clips did Natalia sell altogether in April and May? In this scenario, the model first generates a reasoning step, calculating the number of clips sold in May as 24, half of 48. It then executes a Python code snippet to sum the clips sold in both months, using the external tool to perform the arithmetic operation. The model interacts with the tool, receiving the output from the code execution, which is then incorporated into the reasoning process. This multi-turn interaction allows the model to refine its answer based on both its internal reasoning and the results from the external tool, ultimately arriving at the correct total of 72 clips sold. This example highlights how our multi-turn direct alignment algorithms, MDPO and MKTO, effectively integrate reasoning with external tool usage to enhance mathematical problem-solving capabilities.
What are the practical benefits of your proposed method in comparison to traditional RLHF approaches in enhancing the reasoning capabilities of LLMs, particularly in mathematical problem solving?
The proposed method, particularly through the multi-turn direct preference optimization MDPO and multi-turn KTO MKTO algorithms, offers significant practical benefits over traditional RLHF approaches in enhancing the reasoning capabilities of LLMs for mathematical problem solving. Firstly, These algorithms leverage both positive and negative signals from incorrect trajectories, which allows for more efficient learning compared to traditional methods like RAFT that only utilize positive signals. Secondly, the iterative training process demonstrates consistent performance improvements across multiple iterations, as evidenced by the accuracy gains on benchmarks like GSM-8K and Math, where models trained with MDPO achieved accuracies of 83.9% and 51.2% respectively. Additionally, the MDPO and MKTO methods are specifically designed to handle multi-turn interactions with external tools, which is crucial for complex reasoning tasks that require step-by-step problem solving. Finally, the incorporation of deterministic transitions in the MDP framework allows for a more robust optimization process, leading to better alignment of the model's reasoning capabilities with the mathematical tasks at hand.
Describe the validation process for your method. What datasets were utilized, and what specific metrics did you employ to assess the effectiveness of your approach?
The validation process for our method involved evaluating the models on the test sets of the Math and GSM-8K datasets, which consist of diverse mathematical problems and grade school math word problems, respectively. We utilize these datasets to measure the model's ability to solve mathematical problems effectively, focusing on their performance in multi-turn reasoning and arithmetic operations. The specific metrics employed to assess the effectiveness of our approach included accuracy rates, where we reported the performance improvements of models like GEMMA 1 at 7B and GEMMA 2 at 9B on both GSM-8K and Math after applying our iterative training methods, MDPO and MKTO. For instance, the accuracy of the GEMMA 1 at 7B model increased from 77.5% to 83.9% on GSM-8K and from 46.1% to 51.2% on Math, demonstrating significant enhancements over standard supervised fine-tuning models. Additionally, we compared our results against existing baselines, such as the RAFT algorithm, to highlight the superior performance of our method in leveraging negative signals from incorrect trajectories.
In your results, you mentioned significant performance improvements on Math and GSM-8K benchmarks. Could you detail the specific results achieved and the implications of these findings on the broader field of LLMs in reasoning tasks?
In our results, we observed significant performance improvements on the Math and GSM-8K benchmarks after applying our iterative training methods, MDPO and MKTO. Specifically, the supervised fine-tuned GEMMA 1 at 7B model achieved accuracies of 83.9% on GSM-8K, up from 77.5%, and 51.2% on Math, up from 46.1%. Similarly, the GEMMA 2 at 9B model improved to 86.3% on GSM-8K from 84.1% and 54.5% on Math from 51.0%. These findings indicate that our approach not only enhances the mathematical problem-solving capabilities of LLMs, but also demonstrates the effectiveness of integrating reinforcement learning from human feedback, RLHF, with external tools. This advancement suggests a promising direction for future research in LLMs, particularly in complex reasoning tasks, as it highlights the potential for improved accuracy and reasoning through iterative training and preference learning methodologies.